Howdy, howdy, this is Mr. Potter. Today we're going to be talking about Platonic solids. And so I have 5 examples of a Platonic solid. Right here I've got a tetrahedron called because it has 4 faces. Each one of the faces is a regular triangle. I have a hexahedron, which you would probably call a cube. This is a hexahedron because there are 6 faces. Each face is a regular quadrilateral. And then I have an octahedron because it has 8 faces, and each face is a regular triangle. I have a dodecahedron. Dodecahedron has 12 faces. Each face is a regular pentagon. And then I have an icosahedron. The icosahedron has 20 faces, and each face is a regular triangle. These are called the Platonic solids because they're the only 5 solids that we can make with regular geometric features on each face. So the question is, why are there only 5? So I want to talk about what happens when I try and put shapes together. So if I want to put 2 shapes together, putting 2 shapes together, that's not going to make something that's solid because I'm not going to be able to get a vertex. Remember, a vertex is a corner. So for example, the corner of this tetrahedron. If I want to get a corner, then I actually have to have at least 3 faces. I can have 4. So notice this octahedron has 4 triangles meeting at a point. I can have 5 triangles meeting at a point. The idea here is that I can add a 3rd triangle. Remember, these are regular, so each one of these has an angle of 60 degrees. If I add a 4th, then of course I can fold these together and these sides here will touch. I can add a 5th, and then of course these sides here will touch. But as soon as I add a 6th, this is no longer a spatial object. This is a flat object. Because remember that a full circle has 360 degrees. And so when I talk about a 360 degree angle, I'm talking about something that actually lies flat in the plane. It's not going to be 3-dimensional. So if I'm dealing with a triangle, the only choices that I have are 3 triangles at a vertex, or 4 triangles at a vertex, or 5 triangles at a vertex. Okay, well, let's take a look at squares. Remember that a square is going to have a 90-degree angle, and I can't get away with just having 2. In order to make something that's 3-dimensional, I have to have 3. Each of these is going to be 90 degrees, and when I do that, I get a square. But if I try and put a 4th shape in here, then again, I've got that full 360 degrees. This is no longer a spatial object, this is now a flat object. So if I'm dealing with a square, then I'm only going to end up with 3 at a vertex. And that's the only way that I can do it with a square. So now let's go to a pentagon. Now when I'm dealing with a regular pentagon, gosh, those are hard to draw. Each angle is going to end up being 108 degrees. And again, 2's not going to be enough. I need to have a 3rd. So I've got 108 and 108 and 108, and that adds up to 324 degrees. And of course, I can have 3 of them meeting at a corner. So for a pentagon, I can have 3 pentagons meeting at a vertex. 4 is going to cause some overlap because I'm actually going to be more than 360 degrees. I'm actually going to be at 432 degrees, which is bad. I can't make something that's a 3-dimensional shape with 432 degrees at a vertex. Each one has to have less than that at a vertex. So all I can have is I can have 3 triangles or 4 triangles or 5 triangles at a vertex, or I can have 3 squares at a vertex, or I can have 3 pentagons at a vertex. So these are the only 5 Platonic solids that we could possibly have. However, they're not the only solids one can have, because if you've ever played role-playing games, you know that they always give you this one as well. And of course, this is my 10-sided die, but the thing you'll notice is that each one of these faces is not a regular polygon. This one's actually a kite being a polygon that has 2 long sides and 2 short sides. So the question is, what can I do with these oblong shapes. And the thing is, what's really nice about these three-dimensional shapes, anytime I'm dealing with polyhedra, they have to follow Euler's formula. And Euler's formula is my favorite formula. Because if I take the faces plus the vertices, that's going to equal the edges plus 2. So if I take a look at our tetrahedron, a tetrahedron has 4 faces, and I also have 4 vertices. So if I take 4 plus 4, because I've got a corner up here at the top and then 3 on the base, and then I look at the edges, there are 3 edges from the top vertex to the base, and then 3 edges along the bottom, I end up with 6 plus 2, and that is a true equation. If I deal with a hexahedron, notice with a hexahedron I have 6 faces and I have 8 vertices. I have 4 corners on the top and 4 corners on the bottom. And when I'm looking at edges, there are 4 edges on the top, 4 edges on the bottom, and there are these 4 edges along the corners. So that's 12 edges plus 2, and 14 is equal to 14. What's really nice is that's actually related to the octahedron, because the octahedron has 8 faces, but there's a corner at the top, a vertex at the bottom, and 4 vertices all around. So I end up with 8 plus 6. And if I look at the edges, I have 4 coming from this top vertex, I have 4 coming from the bottom vertex, exactly the same, and 4 along the periphery. So I've got 12 edges again, and that makes something true as well. When I'm dealing with the dodecahedron obviously has 12 faces, and if I look at the vertices, I'm going to see 5 on the top, I'm going to have 5 on the bottom, and then around this ring I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I end up with 20 vertices, and I think you see what's going to happen here. If I wanted to count the edges, I have 5 edges on the top, 5 edges on the bottom, and then I have a total of 20 other edges here. 1, 2, 3, 4, 5, 6, 7, 8, and so forth. I'll actually end up with, 30 total edges. 5 on top, 5 on bottom, and 20 on the periphery. And of course, a dodecahedron we know has 20 faces, but amazingly enough, it only has 12 vertices, because there's a lot of repetition here. I've got 3 on the top, I've got 3 on the top, I've got 3 on the bottom, and then these corners are already tucked, so all I have are the corners around the edge, and there's only 12 of them. And of course, that's still going to add up to 30 plus 2. Great, so what about my 10-sided die? Well, my 10-sided die obviously has 10 faces. And if I look at the vertices, I've got 1 on the top, 1 on the bottom, and if I count around starting at this 0, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm back to the 0. So I've got a total of 20 vertices. If I look at the edges, I know that I'm going to have 5 edges coming down from the top vertex, 5 edges coming from the bottom vertex, and then as I count around, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got the 5 and 5 and 10. So I end up with a total of 20. Wait a minute, I messed that up. Let me recount this again real quick. For vertices, I've got a top and a bottom, which is 2, and 10 around the edge. So that really should be 12. So 10 plus 12 is 22, and 20 plus 2 is 22. My goodness, I messed up that math. Great. But these aren't the only solids. I mean, I could have a 24-sided die. Now, this 24-sided die, if I were to take a look at this, by the way, this is a Catalan solid named after Eugene Catalan, who's a Belgian mathematician. Notice that each face ends up being a isosceles right triangle. So if I take a look at this 24-sided die, I have 24 faces. And for edges, for vertices, I've got 1, 2, 3, 4, 5 on the top. I'm going to have 5 on the bottom. And then I've got these corners in the center. So 1, 2, 3, 4. So I've got 14 vertices. For the edges, I have 1, 2, 3, 4, 5, 6, 7, 8 on the top. I've got 8 on the bottom. And around the sides, I'm going to have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, the ones that make the X, 1, 2, 3, 4. So I had 8 for the top, 8 on the bottom, 4 for the left, right, front, and back. And then I've got these walls, like here between the 4 and the 1, here between the 23 and the 3, here between the 21 and the 24. I've got 4 additional, which is going to give me 36. And if I add that to the 2, I end up with a true statement. And then, of course, we've got a 30-sided die. So I've got a 30-sided die here, which obviously has 30 faces. And if I take the vertices, I'll let you trust me that there are 32 of them. And there are 60 edges. Now, if you want to, you can go to the YouTube page. I'll have a link down below if you want to explore this a little bit more. But this ends up being true as well. So this is my favorite equation when I'm dealing with any type of solid, whether it's the Platonic solids that we started with, or these Catalan solids, or just any old 10-sided die. So once again, this is Mr. Potter. Thank you for watching. Have a great day.